Hello, my dear students, and welcome to the start of chapter number 5 under the title Laser Oscillation and Amplification in our Optical Systems course. Now it's time to combine what we have learned in chapter number 3 and chapter number 4 in order to understand the basic principle of gas laser. So let's first start by recalling some of the main conclusions or the main observations that we have reached in our during the previous two chapters. Okay. First of all, let me highlight that the content of this chapter is a part of the reference Laser Electronics by Verdine in chapter 8 under the title Laser Oscillation and Amplification. Okay, so if we recall chapter 3 under the title of Atomic Radiation, if you remember, my dear students, we have concluded this general equation whenever we start to study a system, a material under optical injection. And we have concluded that if N2 is greater than G2 over G1 N1, which we call the condition of gain, the overall detected in photon intensity after passing through a material will be amplified with respect to the incident laser beam. And we call this coefficient as gamma. Of course, this gamma is a frequency dependent function. You can see that there is a line shape function here, which is a frequency dependent, and we have a lambda here, which is again a frequency dependent. That's why this gamma mu is a frequency dependent parameter. And again, when N2 is greater than G2 over G1 N1, then we have an amplification condition. Or in other words, the stimulated emission dominates with respect to the spontaneous emission and the absorption. Okay, so this is the condition for gain, and this is the gain equation. di by dz, which represents the variation in the intensity according to the dimension of the material, is equals to these gaining factors times the intensity I. Accordingly, you can easily solve such a differential equation, and you can get this term where the intensity I equals to I node, or the intensity at z equals 0, multiplied by exponential e power gamma L, where L is the distance. In a very basic manner, if this condition occurs, accordingly, the gamma factor will be positive, and then you will have an output which is greater than the input because you have a positive exponential, e power positive gamma L. However, if this condition does not fulfill, then you should expect a negative gamma, and here you will have e power minus gamma L, and this will become an attenuation coefficient. It's simply a matter of domination. If the stimulated emission radiation dominates, then the gamma will be positive. If the absorption dominates, then the gamma will be negative. This is simply what we have concluded in chapter number 3, atomic radiation. Then, in chapter number 4, we have go together to the concepts of cavity, where we have an electromagnetic wave propagating between the two mirrors, and we have found together that we have what's called the surviving factor, which is equals to R1, R2 in general. This surviving factor can be R1, R2 e power minus j to KLG, where L is the distance between the two mirrors. However, we of course, this is a propagation coefficient K. However, what we did is that we put the condition of the frequency and the distance, if you remember, so that in resonance, this exponential is turned to be 1. So you have R1, R2, and based on this surviving factor, we have already calculated the photon lifetime in chapter number 4. But the question now is, what if we insert this gaining medium inside the optical cavity or something like that? What if we have the inner medium of the cavity is this gaining medium with a distance Lg? Then let's see what will happen to the surviving factor, or what will happen generally to our system. Okay, so let me start with the general case, or with not the general, actually. Let's just start with the previous case where we have two mirrors. This is R1 and this is R2. And your light is propagating in this manner. So this distance, let's call it LG, to use the same terminology of this chapter. So whenever your electrical field is propagating, there is an effector, which is e power minus j kz, which represents the distance covered by the electromagnetic field. For a round trip, this z will turn it to be 2Lg, one Lg in this direction, another one Lg in this direction. So generally, it is e power minus j 2k Lg. And you have two factors, which is R1 and R2. So generally, this is a general term representing the surviving factor. However, if you put KLG to be multiples of 2 pi, Q2 pi, which is, if you remember, this is a condition for resonance, then this exponential will tend to 1, and the surviving factor will be limited to R1 times R2, if you remember. Perfectly. But the question is now, what if you have the gaining medium here, this Lg, and this is not only a passive medium, it's a gaining medium. Okay, so this is now the gaining medium. Accordingly, when the electromagnetic field will start to move in this gaining medium, or the photons, the intensity will vary in this equation. I of z equals to I node e power gamma z. So in a one round trip, this will turn to be e power 2 gamma z. And we still have this R2 and R1 effect. Accordingly, the new surviving factor will be R1, R2, e power 2 gamma z. This is the new surviving factor, which represents two different processes. Why? Herein, the old gamma factor, where a passive factor, which is e power minus j2kz, and I call it a passive factor because it affects only the phase. It has no effect on the magnitude. It is simply a change in the phase, e power j phi. And an attenuation factor, R1 and R2, because R1 and R2 by default are smaller than 1, so they will negatively attribute to the system. They will attenuate the signal, which is logic, of course. Herein, we have R1 and R2, which are an attenuation factor, because these represent the resistivity of the mirror, or sorry, the reflectance of the mirror. Of course, these reflectance will not be 100%, so you will have some losses here and some losses there, and we already demonstrated. But in addition to this loss or attenuation factor, you can have a gain factor. If this gamma satisfies the conditions that N2 is greater than G2 over G1 and 1, then this gamma is positive, and then this is an attenuation factor. So this S can accept both conditions. It may be smaller than 1 if this losses dominates. And also, it can be greater than 1 if the gain dominates. And of course, this is the case where we are targeting that to have a dominant gain. Accordingly, our target is to have S greater than 1. This is our target. We are targeting to reach an S greater than 1. In this case, you have a gaining medium instead of having a losing medium. If you remember the example I delivered in the part 2 of lecture number 4, when we start together with 100 photons, And I told you that if this 80%, this 80%, after one round trip, it will become 64 photons, and we lose 36 photons, if you remember. Now you can start with 100, and you can end after one trip with 130, with 140, because your surviving factor now is greater than 1, not smaller than 1. Now you turn your cavity to be a gaining medium rather than to be a attenuating medium. This happen again if this term dominates with respect to this term. So simply, if you set S to be greater than 1, or I mean R1, R2, e power gamma Z to be greater than, or e to power 2 gamma Lg to be greater than 1, then this will end up with a system that attribute gain to the intensity of the light. Let me now return back to the presentation slides, please. So this is the condition we are seeking for, to have S greater than 1. If you put this S greater than 1, so you can easily make this condition. Just multiply both sides by line just to get rid of the exponential, and then have this condition. So if gamma is greater than 1 over 2 Lg ln 1 over R1 times R2, if this condition happens, if this condition sustain, then this optical cavity will turn to be a gaining medium. But please, my dear students, take care. Here we have two conditions. Both are important. The first is this condition. This condition is the condition used to make gamma positive. This condition is the condition used to make gamma positive. It's a material dependent condition, not a system dependent condition. It depends on the material, the gaining material, not on the system. Then, on the system level, we have another condition, because simply you can have a gamma positive, but it's still not dominating with respect to R1 and R2. So you sustain the first condition, but you still didn't do it for the second. So what is the condition for the second? This is the condition. Now this is a system level condition. Now you are validating or confirming that the overall system added again to the intensity inside the optical fiber. Another very important observation to this condition is, in this inequality condition, we have left-hand side and right-hand side. The left-hand side is a frequency-dependent parameter, which is gamma. If you remember, I told you that gamma here, yes, gamma is a frequency-dependent because it's simply function in the line shape function, and also it's function in wavelengths. Then it's it's a frequency-dependent function, of course. But let's now return back to the inequality. But here, this parameter is not a frequency dependent. It's 1 over 2 Lg. L is the distance of the gaining material. Ln R1 and R2 is dependent on the mirror. They are not a frequency dependent parameter. So generally, you are inequating a frequency independent parameter with a constant. Let's call it alpha. So it will look like this. If this is gamma, and by the way, this is a very valid shape of gamma. Why? Because gamma is a main function in the line shape function, if you remember the line shape function, which is a probability function. So that's why gamma will look somehow like this. Then if this gamma and alpha is a constant, then you have what we can call a frequency gaining selectivity. What I mean by frequency gaining selectivity, I mean that based on this condition, whenever gamma is greater than A or alpha, then the system will add a gain to the light inside the optical fiber. But if the gamma is smaller than A, then this gain will be reflected, or will be turned to be an attenuation. Accordingly, in this curve, you can divide it into two regions. This region which is the region at which gamma of mu is greater than alpha, then this frequency range, it's better to make it like that. Let me make it in another way. Yes, perfect. This frequency range only will have a gain in the system, because this frequency range is the range at which the condition gamma greater than A or gamma greater than alpha is presented. But in the border ranges, here and here, you will have attenuation, not an amplification, because the condition is not sustained. So simply, not all the frequencies inside the cavity will be amplified. Only the frequencies in this purple range will be amplified. But any frequency outside this purple range will be attenuated. So we can reach, let me erase all this and let's now open the pointer. So we can reflect this on the property of the optical fiber. We have already concluded that the optical fiber have a transmission spectrum looks like that. Now, what will happen, my dear students? Let's see. Let's use the borders again. So we have now these two borders. So per each round trip, resonance inside these two borders will be amplified, which is this one, and this one. However, resonance outside this border will be attenuated per each round trip. And as you can see, even the amplification ratio is different. That's why the central frequency is amplified, or the central resonance is amplified in a greater ratio with respect to those on the left and on the right, because it see higher attenuation, higher amplification coefficient with respect to others. So you can manage to select which resonance you would like to amplify and which resonance you would like to decay or kill based on this management. Moreover, if you are designing a laser and you are seeking for a monochromatic design, what you can do simply, my dear student, is one of two solutions. Either to increase your free spectral range. Let's do it in a better way. Yes. Okay. Either to increase your free spectral range, which is the range between two successive resonance, so that you kick out this resonance outside the amplification zone, and to have only one resonance inside the amplification zone, then your optical cavity will turn to be a monochromatic cavity because you have a single resonance inside the cavity. Or you can narrow down this amplification zone. How you can narrow down this amplification zone? Simply by increasing the threshold voltage alpha, this value. If you push this A value somehow higher, let me make it with a red color, for example. So if you make the amplification as a threshold value here, then your zone will be limited from this point to this point only. How we can increase A? How we can shift up the value of A? It's very easy. If you return back to the equation, you can find it that this is, for example, an inversely proportional function to Lg, which is the distance of the gaining material. So by decreasing this distance, the A threshold will go up, and then you narrow down your gaining zone to select only single frequency and to turn your optical cavity to be a monochromatic cavity. This is a very, very important conceptual understanding of how the gaining medium inside an optical cavity will act to increase the resonance, and how this increasing or how this amplification is a selective amplification in terms of frequency. Okay, now maybe you can ask yourself a very important question. Based on our understanding, this amplification will gonna affect the signal per round trip. That's why this is the first round trip, the second round trip will have a higher peak, and so on. So per each round trip inside the optical cavity, your signal or your resonance will be amplified. That's mean that for an infinity round trip, you will have an infinity amplification. So it's an endless process. Whenever you have a new round trip, you will have a new amplification. You have a new round trip, you will have a new amplification, which is something against the basic understanding of the physics, because usually physically, any physical process should saturate. There is no endless process. It should stop somehow. Then how this gain will be saturated? It's impossible. It's unlogical to have an infinite looping of gain. It should stop somewhere. How this will stop? Okay. To answer this question, we will start to study the most basic model for a laser, for a gas laser, which is what we call the 3-level gas laser. This 3-level gas laser is very important in the basic understanding of the laser concepts, in also answering very important questions related to the theory of laser. So let's start this part together. Okay, this is the 3-level laser. Let me first start to demonstrate the basic concept of this 3-level laser. We have what's called the ground state, which is the minimum potential energy state. And we have two higher energy levels, E1 and E2. Using an external source of injection, the ground states start to inject photon to the level E1 and to the level E2 with the rate R1 and R2. So R1 and R2 represents the rate of injection from the ground state to the first state and second state. And basically, we have the normal 3 transformation operation of electrons defined by Einstein, which are the stimulated emission, spontaneous emission, and absorption. So these 3 processes occurs as usual. However, the stimulated emission process is only limited between E2 and E1 because, as you know, it is a function of the incident beam. Accordingly, the incident beam has an energy which is equivalent to E2 minus E1. So stimulated emission will only occur between the level E2 and E1. But spontaneous can occur everywhere because it's an uncontrolled process of photon. What we are seeking for now, my dear students, is to write a rate equation that can express the rate of change of the popularity N2 and N1 in the level E2 and E1. Let's see how we are going to make it. Okay, so let's start, for example, with the level E2. So I will go back to my white paper and start writing together. Okay, so this is our system, E0, E1, E2. We are interested to write a rate equation for the level E2 and E1. And let's see how we are going to write these equations. So the concept of rate equation is related to find the reasons of either increasing or decreasing the popularity in other level. So for writing the first equation, which is dN2 by dt, so this equation represents the rate of a change of the popularity of the level N2 with respect to time. This equals 2. First of all, let's start to think about what are the reasons for which the popularity of E2 can be increased. So one of these reasons is the injection rate, R2. R2 is the injection rate from the ground state to the energy level E2, which is, of course, act to increase the popularity of N2. So we will add the term R2 in positive. Then we have three processes of transformation from the level E2 to the level E1. The first process is what we call the spontaneous emission. The spontaneous emission generally, my dear students, can occur from the level E2 to the level E1 in a rate we will call it 1 over tau to 1, and can occur from the level E2 to the level E0 in a rate what we call it 1 over tau to 0. So we have two sources of spontaneous emission here. Either to the electron to drop from E2 to E1 and create a photon with an energy E2 minus E1, or the electron to drop from the E2 to E0 and emit a photon with an energy E2 minus E0. So we have here minus, because both will actually decrease the popularity in E2 and 2, 1 over tau to 0 plus 1 over tau 2. Okay, then we have stimulated emission and absorption, if you remember. But the stimulated emission and the absorption are limited to the level E2 and E1. Why? Because this is a frequency-dependent process. And accordingly, the input energy coming from the outside the system, the rho of mu, if you remember the rho of mu, the density of the input laser source, is E2 minus E1. So either to have an electron in E2 and to be absorbed and go to E1, or to have an electron in E1 and drop to E2 and produce a stimulated emission photon. So we will add the term negative sigma I over h mu N2 minus N1. If you remember, this term was previously introduced in our chapter 3 lecture, in the atomic radiation lecture. This is negative represents for the stimulated emission, and negative positive represents the absorption. And here we assume that G2 equals G1, so the term G2 is over G1 is equals to 1, and it is ignored, just for simplification. So this is an overall equation that represents the rate of a change of the popularity in the level N2. Now we can write another equation for N1, but before those, we usually combine these two terms in one term, and we call it 1 over tau 2. So if you go to the Verdin, you will find the equation N2 over tau 2. So tau 2 is the combination of tau 2 0 and tau 2 1, the spontaneous emission from 2 to 1 and the spontaneous emission from 2 to 0. Similarly speaking, you can write an equation dN1 by dt, which is equals to what is the reasons for the popularity for N1 of the popularity of E1 to increase? The first, of course, is the injection, R1. Herein, you should ask me a very smart question. You told us that the stimulation emission is limited from 2 to E2 and E1. Where R1 and R2 come from? R1 and R2 are not as the stimulated emission reason, because they give energy greater than E2 over E1, which is R2, for example. So what is the source for R2 and R1? I believe you will answer by yourself this question whenever you start accessing the tutorial problem. There is a problem in the sheet where we intend to ask ourselves this question: what is R1 and R2, and how we calculate or how we capture R1 and R2, from where we get R1 and R2. Okay, Okay, so let's write the equation. d1 dn1 by dt equals to r1, which is the injection. Then what is other processes? You have again a spontaneous emission which can occur from E1 to E0. So you have minus N1 over tau 1 0. And also you have a spontaneous emission that occurs from E2 to E1, but this will add to E1, not will subtract. So plus N2 over tau 2 1. This is a spontaneous emission, but it will add positively to tau 1. And you have also this stimulated emission and absorption term that will be with a negative sign with respect to equation number 1. So it will be positive sigma I over H mu N2 minus N1. Because herein the stimulated emission will act to increase the popularity in E1, and the absorption will act to decrease the popularity of N1. So that's why it has a different sign with respect to the first equation. So these are the main two equations that are used to express the variation in the population with respect to time for the two energy level E1 and E2. Here are the equations. I think you now can see the equations. Here are the two equations. So this is the rate equation for N2, and this is the rate equation of N1. What we are going to do, my dear students, in the next part of this lecture is that we are going to solve these two equations together. Please don't forget the reason why we start this study. We start this study to answer the question, if the gain coming from the cavity, whenever there is a gaining medium inside, is an infinite gain or it's a saturated gain. So we are going to solve these two equations to answer this question. Another important question that should be answered by the next part also is, do we need 3-level laser system in order to implement a laser? Or in other words, when we study Einstein approach, we study Einstein approach on a 2 energy levels, if you remember, E2 and E1. But when we start to demonstrate lasers, we started with a 3-level. So why we don't have a 2 energy level laser? Why we should have a 3 or maybe 4, as we will see later on in this lecture? What is the constraint toward having a 2 energy level laser? This is also will be answered in the next part, inshallah. So let me now terminate part number 2 till this slide, or till this lecture, and part number 1, I'm sorry, to this lecture. And in part number 2, we are going to demonstrate 3 different attempts in order to solve these 2 differential equations and find or answers our questions. Thank you very much for your concentration, and see you by part number 2.